Like the singer Madonna, RAID has been around since the 80s, and it's something that's really critical in storage IT. So let's go ahead and really focus on RAID and all of the various components of RAID and features and issues there are for us to determine when we're going to implement a redundant array of inexpensive disks. Now, one thing that can get a bit confusing with RAID is you will indeed hear people refer to it in different terminology. When I started this nugget with you, I said it was a redundant array of inexpensive disks. Yeah, that's kind of old school language. RAID can indeed get very, very expensive. So a lot of people will say, no, Anthony, a better way to describe RAID is a redundant array of independent drives. So you'll often see that terminology. I know one thing. Back in 1988, there was indeed a paper that was written called A Case for RAID. It's now a classic, and it really brought this particular technology to the forefront. Remember what we're talking about when we talk about RAID. We can present to devices a logical disk or disks that is made up of a group or set of actual physical drives. So here's physical drive 1, for instance, here's physical drive 2, and here's physical drive 3. And notice here we're presenting one logical drive out to our users. So whenever we're taking physical drives, combining them together in some fashion and presenting a logical drive to our end users, technically we're doing RAID. Pretty cool. Obviously, this helps with the problem of single point of failure. We try and eliminate single point of failures whenever possible in storage and, for that matter, in our overall computing systems. Why did RAID come about, though, other than protection against something like a single point of failure? Well, it came about for performance reasons as well as cost reasons. So cost, performance, redundancy, elimination of single points of failure, these are all reasons why in which redundant groupings of independent drives really became popular. You know what's interesting about this is when we're taking these physical resources and we pool them together and present it as a logical resource, we're doing what? Well, we are doing virtualization. Yeah, this is one of the things that I often point out to in my lectures to new IT people. You know, they're often so jazzed and they think virtualization is so unique and so remarkable. Well, sure, it is really, really cool stuff, but we have been dealing with virtualization for decades in my industry. I mean, you look at a Cisco device, for instance, a big Cisco storage device that can virtualize itself into multiple different logical devices. In Cisco networking, we call this virtual device contexting. This technology existed in the early 80s with mainframes. You could go ahead and virtualize mainframes to be multiple, what appear to be independent systems. So a lot of these technologies that get such fanfare and such attention today, like virtualization, well, we've actually been doing them for a really long time inside our networks. So before we get into any more details, let's make sure we understand these overall components. Once again, we are presenting a logical volume to a particular end user. There is going to be what we call the RAID controller. That is going to be the traffic cop, that is going to be the intelligence that handles this redundant array of inexpensive disks. As we'll talk about in a moment, this particular RAID controller can be implemented as hardware or as software. And sure enough, there's disadvantages and advantages to each of these implementations. Then we have the physical disks themselves. Might be 2 disks, might be 3 disks, might be 8 disks, might be 16 disks that make up what is called a RAID set, or you'll often see the terminology RAID group. So before we move any further, make sure you understand this vocabulary about RAID itself. So now that we understand the basics, the fundamental building blocks of RAID, let's talk about specific technologies that we might see in RAID today. One of them is mirroring. We're going to see this in RAID 1. We're also going to see this in RAID 10. With mirroring, what's happening is we have this logical disk, once again, that's presented to our end users. We have our controller mechanism, and as writes are being done to one of the disks, the identical information is being written to a second disk. I mean, after all, the name of this technology is mirroring. So we're going to have a mirrored copy of the information on another particular disk. Now, what do you think about this? First of all, what immediately comes to mind is, boy, this is going to be a costly approach as far as overhead goes, right? It sure is. In fact, we are going to have the loss of 50% of our capacity because we are indeed taking up this full disk as this disk gets full with information. By the way, what's going on with this disk over here? Well, maybe this is what's called a hot spare technology. Pretty cool, where we can go ahead and should this disk fail, we can have this disk immediately or as quickly as humanly possible or as machine possible can be, we have that particular device fill in for it in the storage infrastructure. But listen, you get the point. If we're using 2 drives and we're doing the mirroring, we lose 50% of our capacity. By the way, as far as performance goes, this is a medium to high performance type of solution. So it's not the best from a performance perspective, but it's not that terrible either. By the way, if we were to lose a disk in the mirrored situation, our RAID is what is termed degraded. And you would indeed want to have some kind of replacement spare technology implementation that you can do in order to get your RAID back from this particular degraded state. So some more great vocabulary here. And again, we're looking at one approach in RAID called mirroring. Now, another very popular RAID technology that you must master is called striping. We see this in RAID levels like 5 and 6, for example. And by the way, we're going to break down the various RAID levels for you, since that's another important piece of information with RAID that you're going to be responsible for in your exam environment. With striping, here's the concept. Once again, our logical volume that's presented to users, once again, are physical disks in a RAID set or group. And this time with striping, what's going to happen is the information is going to be written across the disks. So we'll write some information here, then here, then here. As a matter of fact, we call this piece of information that we're writing a chunk. And then this row of chunks is what we refer to as a stripe. Obviously, we're going to have a particular stripe size, an amount of information that is striped across the disks, and how many physical disks we have in the RAID set is going to give us a particular stripe width. Now, a lot of people say striping, just plain striping, writing the data across these different disks like this, can't even be considered RAID. Yeah, they say, wait a minute, you're getting 0 fault tolerance here. So you're not really doing RAID. Yeah, think about it. If one of these devices is to fail, we cannot reconstruct the information that has been stored. So what is an appealing thing about simple striping? Why would we ever consider such an approach? Well, how about very high performance? Absolutely. So when we stripe the information across the multiple disks like this, we get an awesome high performance read-write operation. Something else to consider here is the fact that we're losing 0%. Yeah, there is no loss of capacity here. We are utilizing all of these disks that we have grouped together in the RAID set. Now you're probably familiar with striping with parity. Yeah, when we add parity information, we can reconstruct information that might be missing. So this is great. So we are going to, once again, have our controller, we're going to have our logical volume, we're going to have our physical devices. We're going to write information here, for instance. We're going to write some information here, and then here we'll place parity information. That parity information can be used to reconstruct things in the event of a disk failure. So now we are getting into a situation where we have resiliency. We have this group of disks, and one of those disks can fail, and we may experience degradation in performance, but at least we have not lost information. Combine this with this concept that we talked about earlier of hot spares, and it really gets exciting. This disk could completely fail, and everybody is still receiving the information just fine from the RAID conglomeration here. And then we have a spare device in an automated fashion that picks up for the device that failed. The parity information is rebuilt, and everything starts running beautifully once again. The hot spare concept could literally involve a physical disk which is sitting there waiting to introduce itself into the RAID set, or it could be a virtualized solution. Virtual hot spare technology is becoming the rage. Let me clear off my marks here, actually, and let me describe what this concept of virtual hot spare is all about. Imagine if you reserved a section on each of these disks, and this reserved section on each of these disks could be utilized collectively like your hot spare. How cool. So our virtual spare technology is just portions of the physical disks that we are setting aside for that particular function. So a very interesting way in which to provide hot spare functionality. But you know what we haven't elaborated on yet? And that's hardware versus software RAID controllers. Yeah, we know that there has to be this point in the RAID system of the intelligence, of the particular circuitry, of the intelligence to make sure the RAID is being implemented correctly. You might think, well, I want to do that in hardware. And I want to do that in hardware because hardware is always going to give me higher performance than software. And look, you're basically right. Absolutely, if we use hardware, we can get things like non-volatile RAM caches right built inside that hardware RAID controller. We can have the device have its own CPU processes, CPU resources, so it doesn't have to bother a host system for this. But realize, this comes at a price tag. So one of the reasons we may not want to go with a hardware controller RAID solution is because it costs too much for our particular installation. Also, there's going to be less flexibility with what that particular RAID system can do and how it could be configured. Software RAID, often called poor man's RAID, is indeed going to be lower cost. And it's, of course, going to have performance issues compared to hardware RAID. It's going to need to steal resources from a host system. But you know what's great is software RAID solutions are indeed becoming more popular nowadays because think about your computing systems. They're starting to get more and more powerful. So oftentimes they do indeed have resources that they can gladly surrender to the RAID system in order for it to do its job. Also, software-controlled RAID tends to get more important and more prevalent these days because of software-defined networking. More and more, we are thinking about software mechanisms controlling the way in which our network actually operates. Now, one thing to watch out for when it comes to software-based RAID solutions is that they're obviously not going to be able to protect the boot drive that contains the operating system that is responsible for hosting the software-based RAID solution. So be aware that we can get into issues with protecting all of our drives with such a solution. Now, if we're going with the highest performance solution and we don't care about costs, we're looking typically at hardware RAID solutions, and really we're looking for oftentimes array-based RAID solutions. These are very sophisticated, very high performance. We talked about array-based storage earlier on in the CBT Nugget course. Just realize that we can be talking about this massive RAID array that has its own operating system and that can run at the very highest levels of performance and the most amazing fault tolerance mechanisms built in. So keep in mind, when we're talking hardware-based solutions, oftentimes we're talking about a full, sophisticated, relatively expensive array-based RAID solution. So as you might guess, for the CompTIA Storage Plus certification, you're going to need to know some of the most important official levels of RAID, and we start with one that's pretty controversial. Is it RAID or is it not RAID? Well, I like how it gets RAID level 0 as a designation. It's striping. We described striping earlier, didn't we? We were going to write information here, write information here, write information here, but we're not using any parity information. So if we have a failure of a particular disk, we're in big trouble. Notice there is no redundancy, and therefore the designation of 0 is quite appropriate. You could argue this isn't RAID at all. Sure, we get high performance, sure we haven't lost any capacity on the disks, but we're not redundant with RAID 0 or striping. In fact, where you tend to see this done is nested inside some other solution that is providing us with redundancy. So let's move to something that gives us redundancy, and that is, of course, RAID level 1. Great news, you already know RAID level 1. It's that mirroring technology that we spoke of. So we are writing information to, let's say, this physical disk, and this information is being mirrored to another disk in the RAID set. We love mirroring from the perspective of performance, certainly, the fact that it does indeed give us redundancy that we're looking for. But what's the big problem with mirroring? Oh yeah, that capacity loss. We said there's a whopping 50% capacity loss because we are indeed duplicating the information in its entirety to another disk in the RAID set. RAID 5 is striping with rotating parity. Interesting. So we write some information here, a chunk right there, then a chunk right there, and then our parity information is written on disk 3, physical disk 3 in this example. Then we write some information here, striped, and then the parity is written here, and then information is written there. You get where we're going here. Parity information might be written here, then a chunk here, then a chunk here in that particular stripe. This is called rotating parity, RAID level 5, as I said, or sometimes it's called distributed parity. RAID level 5 allows us to lose a single disk, and we can still recover that particular information. That's one disk can be lost. Now, there's the loss of some capacity here, right? Certainly not the capacity loss that we saw with mirroring. In fact, there's an equation that you can use to calculate the approximate overhead that you're going to have in this rotating parity example. Let's say you have one chunk of parity being written and you have 8 total discs. You have 1/8. You multiply that by 100, that gives us 12.5%, and that's the overhead that we can experience thanks to the parity information. So the overhead or loss is 12.5% of our theoretical total capacity. Now let's bump up to RAID 6. Let's do something cool. Let's add some more disks into our RAID set. I'll add 6, for example. All right, great. Now what we'll do is we'll write a chunk, we'll write a chunk, we'll write a chunk, we'll write another chunk, and then we'll do 2 parity block information pieces. And by the way, like RAID 5, we'll rotate that parity information. So we can do chunk, 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 parity, parity, chunk on the next striping across these disks. Guess what? With RAID 6 and the dual parity approach, we can now lose 2 disk drives and we'll be okay. It turns out that if we're dealing with large disks in our set, specifically 1 terabyte or larger disks, then RAID 6 is really going to be a great solution. This has to do with how in which the failed disk needs to be rebuilt. So very large disks favor a RAID 6 dual parity approach. Your overhead calculation is going to be pretty much the same when you're estimating that. Here in this example, I have shown a 2/6 or 6 plus 2 type system. This is 2 chunks of parity information written over 8 disks total. I have 6 disks here. Let me draw 2 more. There we go. So if we have a 6 plus 2, an 8-disk system, that's 2 chunks of parity written across 8 physical disks. We multiply this times 100, and we get a 25% overhead thanks to the dual parity information that's written. So when you are calculating the overhead, once again, we can take the total disks divided into the chunks of parity that we write, multiply that by 100, and we get a good guesstimate as to the overhead loss due to our parity information. Now you might look at this too and you might say, Anthony, I don't care how big my disks are. I want RAID 6. I mean, this is awesome. I can lose 2 disk drives. Performance is pretty good, and that's where we're going to be careful. You see, the read performance on RAID 5 and RAID 6 is pretty decent, but write performance does indeed suffer. In fact, write performance suffers worse in the dual parity environment. So performance is the issue, especially write performance, and in fact RAID 6 would be a very poor choice if we had a lot of small block random writes that our disk system had to do. So from a performance perspective, is there anything better than we could do than RAID 6? Yeah, we could engage in the next level of RAID that we want to talk about, and that is called nested RAID. Nested or hybrid RAID is RAID 10. You'll often hear people say this is RAID 1 plus 0. By the way, note this is different from RAID 0 plus 1. What was 1 and 0? Do you remember? 0 was striping and 1 was mirroring. So with RAID 10, we mirror, then we stripe. With RAID 0 plus 1, we stripe, then we mirror. There is indeed a difference. We're talking here about RAID 10 or RAID 1 plus 0. So think about what we would do. We would mirror. So we would have 2 physical disks and we would mirror them. We would then have 2 other physical disks. We would mirror those. We would then have 2 additional disks and we would stripe these mirrored sets across those two disks. So again, here is RAID 1 being done on these physical disks, and then RAID 0 being done, the striping. Notice here that we do have a 50% capacity loss. So this is an expensive solution, but it gives us amazing performance. Notice we could also potentially lose two disks. We say potentially here because it would have to be one of these and one of these. Obviously, if we lose both disks in that mirrored environment, we're in big trouble. But potentially we could have two disks fail under this nested arrangement and still be okay. Well, that sure was a lot of information, and I know you're going to want to review that. Make sure that you're ready for a certification exam environment on the topic. What I'll do is I'll be sure to give you some questions as pop quizzes in upcoming nuggets in this course on RAID. We're out of time in this particular nugget, but look forward to those questions coming up soon. As always, I sure hope this nugget was informative for you, and I'd like to thank you for viewing.